Okay, hold on one second. I'm going to put my ugly mug up here in the corner real quick. All right, I'm getting a lot of, as you can see here, we've got exercises 9 and 10, and we'll look at 11 too from the buoyancy thing. I think we just need some because I'm getting tons of questions in there, and they bother me because they're like, I'm like, really? But then when I think about it, I'm going, well, this has been kind of dorked up anyway this last 4 weeks. So I'm going to go ahead and I think if you watch the actual videos that went with it, it should be okay, but maybe not. And I know that some of you are like, I don't want to watch all these sports lectures. I just want to get to know. I just want to know what I need to know for the test, and because I know these questions, some of these questions might be on there or something like it. So you're right. So I'm going to do homework 9 and homework 10 and homework 11. All right, and each one will be divided. It won't. Each one will be about a 15-minute video, and we'll take it from there. Okay. All right. So let me get my mug out of the corner here, and let's just get started. So let's go ahead, and I'm going to take this just like I you all. All right. Force completion. Test is due May 1st. I hope people have already started this. Okay, so I'm not going to bother with that. Okay, the wheel of a car has a torque. The engine of the car applies a torque of 295 times. Stupid. I copied these off something, and that's the way it comes out, and I apologize. To this wheel, which does not slip against the road surface. That's an easy one. I mean, that's R times 295 times 0.35. So that's a gimme. All right, here was one that screwed people up. Okay, and I think I talked about this one. So a meter stick is pinned down on a frictionless surface, much like in slide 9. And I don't even know if the slides correspond with. I'm hoping they do. But this time it is pinned at the 30 centimeter mark. 0 is to the left and 100 centimeters to the right. A downward direction force of 8 newtons is applied 15 centimeters at the 15 centimeter mark. Where do we apply a downward force of 5 centimeters to prevent the stick from rotating? Put your answer in meters. Okay, we did that. Now remember on this one, so on question, whoops, forgot to turn on. I thought I had everything ready to go. Come on now. Jiminy Christmas. All right, so here we go. So on this one, question 3, and some people missed this because this is at 15 centimeters, 8 newtons at 15 centimeters. And where do we do the 5 newtons over here? You know, what's this x distance with 5 newtons to keep this thing from rotating? All right, it will not have an angular acceleration. So we just said, well, 8 times 15 is equal to 5 times x. When you do that, you wind up with 8 over 15. Now you might, well, you didn't convert it yet. It doesn't matter right now. Equals 24 centimeters. Okay, but the actual distance then, if this is 24, then this is at 30. This is the 15 centimeter mark, and this is at 30. Then this would be at 54 centimeters, which is equal to 0.54 meters. Okay, now the next problem kind of screwed people up. It said, well, what's the force on this pen? And I think where people were confused is they were thinking, well, in fact, I know where confusion came because one of your students came to see me on Friday, and he made a good point. He was like, I thought they were talking about the force that's drilling in here with the screw that's in the table or whatever, the pin. No, not that force. That's a whole different thing. We're just talking about the force in the y direction on this pin. So we've got 8 going down, 5 going down. I need 13 going up. Oh, I don't mean to give you the answers on this either. I just kind of want to set it up. Yada, yada, yada. You can figure that one out. All right, now, assuming CD is a uniform circuit to determine the angular acceleration. Well, we know angular acceleration already, right? So for problem 5, 6, oh, it's a bit me. 6 is angular acceleration is equal to our change in omega, our radial speed, divided by the change in time. And I think they gave you that. I think it went from omega naught is equal to 0 and omega final is equal to 21 radians per second. I think we can do that. All right. And then what was the next question? Next, it said, using the information in question 6, what is the moment of inertia of the disk? Okay, some people were confused by this. They were going, so here's what they're trying to do. They're trying to figure out, well, what's the torque? This was what was going on in question 7. This was wrong. Some of the thinking, going on in question 7 was like this. It's like, the moment of inertia, then the torque is equal to I times alpha. I don't really know the torque. I guess I got the radius, but I don't know the force that was applied at that end or the torque that's created by this. So I can't. So you were stuck because you had this, but you didn't have this or this. And you're like, hey, I've only got one equation. No, that's not what I was talking about. I just wanted you to find the moment of inertia I of a disk, of a circular disk, which is equal to 1/2 mr squared. That's all I was wanting you to do there. Okay? Where I think they give you, let's go back and look at it real quick. I think they give you 17 grams, 6 centimeters. So 0.06 meters, 0.017 kilograms, and you plug it into that. Okay, then on 8, it says, continuing with the information for problem 6, how much mechanical work? Okay, now we got to remember, mechanical work. So for problem 8, mechanical work, and again, I got some thinking on it that was good, but not quite right. Mechanical work, the work done is actually equal to the torque times the angle, the number of radians that it goes around. Just like force times distance gives us work, angular work is equal to tango times or torque times alpha, which is equal to, but we also know that work is what? A change in kinetic energy. Aha! So you got the kinetic, so you got the moment of inertia here, and since it's not, there's no translational, the translational velocity is equal to 0. In other words, it's not rolling along a street. It's in a pin. Well, it looks like this. Looks like this. All right, it's not going anywhere. Should have brought that in to class. All right, and it's not going anywhere. So we just go, okay, well, cool. Then the change in kinetic energy is equal to, and work is equal to 1/2 I omega final squared, which is up here, minus 1/2, and you found I here, minus 1/2 I omega naught squared, which omega naught is equal to 0, so that goes away. All right. Now the next one was kind of a tricky one. Problem number 9. A little bit tricky. Not too bad. I like it though. It's a great problem. Find the speed of the ball at the top of the rise. Okay. So a bowling ball. Notice they don't give us a mass, so that must cancel somehow. I'll bet $1 to a donut that sucker cancels. So we're talking about energy. Okay. The initial translational speed down here is 3.5 meters per second. Now notice they drew the vector smaller up here because of course it's going to go slower up here. All right, we want to find the speed of the ball. Notice they don't say velocity. They just give the speed because we're talking scalars, we're talking energy. All right? Sound like Alec Baldwin in Glengarry Glen Ross. So what are we talking about? What are we talking about? Get them to sign on the line that is dotted. Anyway, so here we go. No biggie. Once we get used to some of the screwy algebra that goes with this, here we go. We've got, so we got the bowling ball rolling along. This initial was given, and I can't remember now what it was. Oh, this is confused. 3.5 meters per second. Wow. I should have cleaned this up for you. I apologize. Okay, so it's 3.50 meters per second. No wonder it was so hard for you to read. Okay, my bad completely. All right, so it goes up to the ramp. 0.60 meters is up here. Now it's going a little bit slower. All right, now this isn't a block sliding. If this was a block sliding, we'd just say 1/2 mv squared is equal to 1/2 mv final squared plus mgh. Piece of cake. We'd be done. All right, but that's not the case here. We've got a bowling ball sliding, so we've got to do this. We've got to say, okay, we've got the energy before is equal to the energy after. Well, it's got a translational velocity, so it's 1/2 mv naught squared, plus it's got a rotational energy, kinetic energy, 1/2 I omega naught squared, and that's all that's down here, because mgh is h naught is equal to, let's write down our variables that we know. H naught is equal to 0, v initial is equal to 3.5 meters per second, omega naught is equal to 0. Omega naught is actually equal to something. Omega naught is equal to V over R. Okay? You're going, but wait, they didn't give me R. Hold on. But this is going to equal 1/2 mv final squared plus 1/2 I omega final squared plus mgh. Okay, we need to know the speed that it's going when it gets up to the top. Well, let's take advantage of this. Let's take advantage of this, and also this thing. I is equal to 2/5 mr squared. And a lot of stuff is going to cancel. Let me show you real quick. So we've got one, but you're going to run the numbers here. 1/2 mv naught squared plus 1/2 times 2/5 mr squared, that's my I, times omega naught squared, which is v naught squared over r squared, which is equal to 1/2 mv final squared. Now we write the same thing again, plus 1/2 times 2/5 mr squared, v final squared over r squared. Look at that. You see some stuff that might cancel here? Plus mgh naught, which is given, mgh final, which we know what that is. All right. So look, that cancels, that cancels. That cancels, and that cancels. The rest is dibbling and scribbling with some algebra. All right? Take your time. So cancel the r squareds and cancel the masses. All the masses go away. This is all given. This is a number over here. Oh, look at this. This cancels too. And then it'll all work out. Then cancel the m's, and you're good. All right, so that's exercise 9.